target in our gases unit. We will be looking at this last sub-target here, explaining the conditions under which a gas would behave most ideally. So what is an ideal gas, or what are ideal gases? Well, simply, ideal gases are gases that follow the gas laws perfectly. So those laws that we've looked at, the Charles law, Boyle's law, Gay-Lussac's law, those relationships, pressure and volume being inversely proportional, temperature being directly proportional to pressure and volume, and then there's also a gas law called the ideal gas law, which we'll hit up here shortly. Those gases that follow those relationships perfectly, those are ideal gases. There are three properties that make a gas an ideal gas. They are A, that particles occupy zero volume. And you might be thinking, wait, how is that possible? How can a particle occupy zero volume? Well, in reality, it can't. So, really, you might be thinking, well, these ideal gases, do they even exist? The answer is kind of no, and we'll address that as we go on here. But just going along with this idea here, when we say particles occupy zero volume, that would be, in an ideal world, really what we're getting at here is that the particle volume is so insignificant compared to the entire volume of the gas, then we have a gas that can behave quite ideally. So just picture this. If we had these two gases here, one where I have not so many particles in a container, one where I have a lot more particles, the volume of these particles occupies a much smaller fraction of the overall volume of the gas. So we would predict that these here would behave more ideally than these here on the right. Another thing you can think about is the particle size if they're smaller, and we'll talk more about that a bit later in the lesson here. Alright, so the first property is that these particles are super tiny, that they occupy virtually zero volume. The second property of any ideal gas is that these particles, they experience no interactions with each other. In other words, what we mean by that is that the particles, there are no attractive forces pulling them together, there are no repulsive forces pushing them apart. So if we look at this picture here, this can help us understand what we're talking about. Here on the left we have an ideal gas where these particles, they are completely separate entities. They're not pushing on each other, they're not pulling on each other. Yes, they're going to run into each other as they move, but there's no forces between them. Over here, we have what we call a real gas. In other words, it's not ideal, where if we focus on this particle in the middle, perhaps it's being attracted to some of these particles, maybe it's being repelled from them, which might cause it to have a different sort of motion than if there were no forces acting on it, other than gravity, which there's always acting on it. But we can see over here we have a situation where there are forces between the particles, which would mean it's not ideal. The third property of any ideal gas is that the collisions that the particles experience are elastic. And what that means is that the kinetic energy is conserved. In other words, whatever kinetic energy is in the system before the collision, and whatever kinetic energy, say, two particles have in a collision, the kinetic energy that those particles have will stay the same after the collision. So if we think about a scenario here where we have a gas particle, which I've signified here with this green dot, and this line here, say, represents the wall of the container. This particle is going to be moving around, and let's say it's moving at 500 meters per second when it hits the container, which you might be thinking, that seems really fast. But actually for gas particles at room temperature, that'd be about average. It's about 1,000 miles per hour, a little more than 1,000 miles per hour actually. So if it's going 500 meters per second when it hits the wall, when it rebounds, after it collides with the wall, it would still be moving 500 meters per second. That would mean that the kinetic energy is conserved. So in ideal gases, we have particles that take up zero volume. We have particles that experience no interaction with other particles other than their collisions. And then we have collisions that are elastic, meaning the kinetic energy is conserved. So a question that I kind of addressed earlier was this: which gases are ideal gases? And the answer to that is none, really. there are no gases that behave perfectly ideally. You might be thinking, well, why do we even have this idea of an ideal gas? Why do we study it? Well, it's because many gases can behave very, very closely to ideally if the conditions are right. And so what that means then is those gas laws that we have developed as far as the relationships, those are an excellent approximation in lots and lots of circumstances. So it's not a waste of time that we have studied that stuff. It's not a waste of time that we're studying these things called ideal gases, because they're excellent, excellent approximations for gases in lots of different circumstances. So what we want to ask ourselves then is, what are these conditions that lead to a gas behaving most closely to this idea of ideal gases? Well, we'll just consider each of those points of those properties that we talked about earlier. So what condition or conditions would lead to particles occupying a very tiny, tiny volume of the overall volume, or what we call an insignificant volume? Well, if we go back to that same picture we looked at before, where we have these two gases, let's say that they're probably the same gas, and in one of them we have fewer gas particles than in the other. These gas particles here occupy a much smaller fraction of the overall volume of the gas. Well, think about what the difference is between this gas here and this gas over here.
Jacob Rupke,
The difference here is obviously in the pressures. The gas on the left will exert a much lower pressure than the gas on the right because there's so many fewer particles, where there's going to be less collisions. So one condition that would lead to a gas behaving ideally would be, A, if the gas is made of small particles. Just imagine if these particles were much, much smaller on either side. If the particles are smaller, then they're going to occupy a smaller volume of the overall volume. But then also, if the gas is at low pressure, the lower the pressure a gas is at, the more ideally it will behave. This is simply because as the pressure goes down, the gas particles take up less and less space in the overall volume that the gas occupies. Now let's look at that second property. What conditions would lead to the interactions between particles having little effect on the particles? So we said that ideal gases, there are no attractive or repulsive forces acting between the particles. In reality, most gases are going to have some sort of attractive or repulsive forces going on. So if we think about a scenario here where we have a gas particle and it has some velocity, here I'm showing it moving to the right, and there's another gas particle close enough that there can be a force between them. Let's say these two particles have an attractive force, where this particle that's moving to the right is attracted by the particle down here, so it's going to get pulled this way. Well, this particle, as it moves past the other one, its direction motion will probably get bent down this way ever so slightly. But ask yourself, what if this particle was moving much faster? What if that particle that was being attracted here on top was going a lot faster, something like so? Well, if the particle is moving fast enough, that force that's pulling it is going to have very little effect on it. In fact, we could get the particles moving so fast that it'd be as if there's almost no attractive force there. So one thing that we can do to make these particles go faster, or what we can do, not just one thing, what we would do to make them go faster, is to increase the temperature. So if the gases have high temperatures, that means these particles are moving around very quickly. And the faster they move, the less of an effect these attractive or repulsive forces, either one, will have on their motions. The other thing that we could do is, if certain gases, there'd be very little attractive or repulsive forces between them. So if we had a gas that did not have many of these forces, whether they be attractive or repulsive, then we would have very little interaction. So if we could have gases at high temperatures, and if we can have gases with no or very small intermolecular forces, that's what we call these forces acting between particles, intermolecular forces, then the gas is going to behave more ideally. These same arguments that we're talking about here would also be true for the whole idea with elastic collisions. The faster the particles move, whether it be about the collisions with each other or the collisions with the container, then there's a better chance of those collisions approaching that that elastic scenario that we talked about. So in summary, we've said that ideal gases are gases that perfectly follow the gas laws. Ideal gases have particles that, I'm going to pause the video here. I want you to think about this, fill in what you think should go next. So hopefully you said these particles occupy zero volume, they have no interaction with each other, and they experience elastic collisions. We learned that ideal gases do not really exist. However, that gases can behave close to ideally when we have certain conditions. Again, pause the video, see if you can remember what those conditions are. Hopefully you identified the following. We have identified that gases behave most ideally when they're composed of small particles, when the gases are at low pressures, when the gases are at high temperatures, and when the particles have no intermolecular forces, or at least very small intermolecular forces acting between them. Alright, this concludes all of the lessons for this first learning target here. You can take a look at each of these subpoints. We have hit all of them up, and we should now be ready to do some assessing on this first learning target.